All right, guys, welcome. It is 8 o'clock. Let's go ahead and get started. Before I forget, please remind me at the end of class if I don't remember to do so. I have a big old stack of papers to get back. So just be sure to remind me in case I overlook that. All right, so today is a Q&A review day. So if you have questions that you would like to ask about problems or concepts or homework or anything, go ahead and ask them. For you Zoomers out there, if you want to put something in the chat, that's fine. It may take me a few minutes to get to it if I'm doing something else, but I will do my best to get to it in time. So yeah, you got questions? Hopefully I got answers. Y'all ready? You know, I don't think in 16 years I've ever asked that question and gotten really enthusiastic responses. Keep thinking one of these times it's going to happen. Can I go over how to show something as an ortho-para director or a meta director? Yes, I can do that. So typically, whenever you're asked to prove whether something's an OP director or an M director, that means you're going to have to draw a bunch of resonance structures, right? Specifically, that means you're going to have to draw resonance structures of the hypothetical carbocations that are made when you substituted each of these positions. And remember, basically what you do is you draw all the resonance structures out, then you look to see if any of the groups have special stabilization or special destabilization. All right, so let me think of one here. Trying to think of one I haven't done already in class, but I can't really remember. Let's try this one. Let's try toluene. All right. So what we would want to do is we would want to show the carbocations that would be made once that E+, that electrophile attacked. All right. So like I said, we're going to do this for ortho, meta, and para. Okay. So if we had an ortho attack, an electrophile is going to attach itself right there using these electrons, and it's going to leave a positive charge right there. All right, and then you draw resonance structures. How could we get the next resonance structure for this? What would we move around? Pi bonds at the top, right? Try to satisfy the charge. So this pair of electrons would swoop over here, leaving a positive charge at that carbon. And you keep doing the merry-go-round, right? This pair of electrons could swoop in over here. And give you that one. Okay. Now, sometimes we can draw a fourth one. Can we do that here? No. The only time you can ever draw a fourth one is if you have a positive charge here and a heteroatom here, like an oxygen or nitrogen or something like that, that has unshared pairs of electrons. We don't have that here. So we just get 3, right? Then we start over, do the same thing for meta. So if we get a meta substitution, our initial carbocation is going to be that because we're using this pair of electrons. Bring this pair down, satisfy the positive charge. Get another one, and keep doing the merry-go-round. I'll try to fit all these together. Okay. Para, do the same thing except at the parent position. E comes in. Again, attaches with this pair of electrons. So it leaves a positive charge here. And then just keep using the merry-go-round to satisfy the charges. This pair comes down, whoops. This pair comes down over like that. And you have one. Yeah, so in this case, you have 9 different resonance structures, 3 for each hypothetical position. Notice you guys are still copying this down, so I'll give it a pause. Take a look at those. All right. Remember, what we're looking for is Do you have something particularly stabilizing or something particularly destabilizing? And really, in essence, you're just going to be looking at the ortho and para. The meta is just sort of a baseline that never really has much of anything extra stabilizing or extra destabilizing. It's just kind of consistent. It's the ortho paras really that are going to be stabilized or destabilized. So if the ortho paras are stabilized, then it's an ortho para director. If they're destabilized, then meta wins by default. All right. So do you notice anything particularly stabilizing or destabilizing in any of the ortho or para structures? Yes?
The positive being so close to the partial positive.
Where's the partial positive?
Oh, I got confused.
That's okay. Yeah, the carbon of the methyl group actually does not have a partial positive here because there's nothing electronegative pulling off. That does happen though in some other species though. Yeah. Like if you had a carbonyl group or something like that. Any ideas? Sometimes these are obvious, like when you have 4 versus 3 structures. Other times it's a lot more subtle. This one's a little more subtle, I think. Any ideas? Going once, going twice. All right, let me give you a hint. Take a look at the types of carbocations that are formed in each of these structures. Do you see any that might be better than others? What's that? Why meta?
Because the carbocation sit next to the toluene on the other ones.
Because what? I'm sorry.
The positive pulls away from like the toluene and the electrophiles on the ortho pair.
The electrophile is actually not going to matter here. And the CH3 of toluene doesn't have anything electronegative, so it's not going to have any particle. So it's not going to be that in this case. I saw somebody's hand up. Who was that? Somebody over here. Really, am I imagining things? Matt, was that you that had your hand up? Are you sure? Now I'm sort of worried about my own mental stability. What type of carbocation is this? What's that? The secondary allele specifically, right? What type is this one? What type is this one? Secondary allele. What type is this one? Ah, yeah. Tertiary allele is better than secondary allele, right? Both ortho and the para have this tertiary allele carbocation. That's a good thing. And that adds extra stabilization. So in this case, this would tell you that a methyl group is an ortho para director. And you already knew that from the table, right? But this proves it. This tells you why that's the case. Yeah, Josh.
So if we have a tertiary meta, then that one would be more stable. That would be better.
If you had a tertiary meta,
Yeah.
you're not going to have a tertiary meta.
So when do we? How do we know that it's a meta? It's through, like say,
You know it's meta when something is destabilized with ortho and para. Meta never wins. I guess it does win. It never wins on its own. It's like that team, if you follow sports, it's like that team that loses the game, but their second place team lost, so they won the division, you know, so they get kind of that empty celebration. Yeah, that's why. So that's why you really want to look at the ortho-para situation much more closely than the meta, because it's all going to come down to this. Like, and I'm not going to draw all of these out, but let's just say we had, I don't know. Let's say we had like an aldehyde group up here or something, right? And let's say we put an electrophile here. And this was one of our resonance structures, right? This is an ortho substitution. This structure is destabilized. Why is it destabilized? Lisa, why is it destabilized? You have a strong partial positive over there. So positive plus a strong partial positive right next to each other, that's not a very favorable situation. So if you drew out all the resonance structures for ortho, meta, and para on this one, you'd have 3 orthos, you'd have 3 metas, you'd have 3 paras, but each of the ortho and para would have this situation, which is, you know, not very stable. So that means meta sort of wins by default because it doesn't have any of that destabilizing situation going on in its structures. Did I answer your question, Josh? Yeah. Okay. Cool. All right. Good stuff. What else would you guys like to talk about? Yep.
What was the formation of amines and amines?
Formation of imines and amines. Yep, I can do that. Okay. So basically, when you make an imine or enamine, you're going to need 2 basic ingredients or 2 basic pieces. One of them is going to be an aldehyde or a ketone. They both work. And the second one is going to be some sort of amine. Now, the type of amine that you use will determine whether it makes an imine or an enamine. We'll just show this with acetone. Acetone and this. I forgot you also need mildly acidic conditions. Okay. So that's the basic setup for one of these. All right. Now, what type of amine is this? Primary, secondary, or tertiary? It's primary, so keep this in mind. We're working with a primary amine. All right. Let's go ahead and work through the mechanism. All right. What's going to happen here? What do you think can happen? Nitrogen and your amine is going to attack their carbonyl carbon. There's no leading groups because it's a ketone, so it's going to be an addition reaction. All right, you end up with that. That's got both a positive and a negative. How can we satisfy both of those charges in one fell swoop? Yeah, proton transfer, absolutely. You can just simply transfer a proton from that nitrogen to the oxygen, and that makes both of them neutral. And it makes that intermediate structure. It's called a carbanolamine. All right. So that is what happens after attack of your amine. Now, one thing we haven't seen come into play yet is the H3O+, right? This is where the H3O+ comes in. That's hydronium, so we know it's acidic. All right, what do you think that acid is going to do to your carbonylamine? Acids like to give up H's, and OHs are very accepting. So you're going to donate the proton to the OH. Okay, that makes water. What do you know about water? Good leaving group, yes. So water's going to leave. Now, when water leaves, it takes these electrons with it, so that would leave this carbon electron deficient. In turn, don't forget, even though we haven't been drawing them, there's a pair of electrons sitting on nitrogen. This pair of electrons can swoop down and fill the void with a double bond. So you make a carbon-nitrogen double bond at the end of that step. All right, and there's only one more step in the mechanism. We need to get rid of that positive charge. So what can happen is your H2O that was left over from your acid can come back, grab that H, and you end up with that. That is your imine. Okay? So, aldehyde ketone plus a primary amine gives you an imine. And that's how the mechanism works. Okay? So, anytime you see this and you kind of forget, what's going on, you can definitely work through the mechanism and figure it out. You can also predict the product of these reactions pretty easily too. All right. If you look at this, ignore all the intermediate stuff, just look at the products and reactants. Really, anytime you have this, if you recognize this as being something that's supposed to make an imine, to get the structure, all you got to do is just replace the oxygen with the nitrogen and carbon chain. Just leave off the H's. But the double bond is still intact. It's just going to be the nitrogen in this case. So there's a little bit of a shortcut if you're just looking to predict the product. Although, you should really know the mechanism. Okay? All right, any questions on that one? All right, let me do an enamine. Now, what's the only difference as far as reagents here to make an enamine? What's that? Yeah, secondary amine instead of a primary amine. Yep. Let's see. Well, I'm using aldehyde in this case. Okay, so aldehyde or ketone plus a secondary amine. And this time, that's going to give you an enamine. All right, I'm going to go through the mechanism, and you're going to see it's very, very similar to the last one we did, with one important difference towards the end. All right, for the most part, it's exactly the same, right? Your amine's going to attack your carbonyl group. You get a proton transfer. And you get the carbanolamine, just like last time. I'll catch up. So that's what happens with your amine. And now, again, just like last time, that's where your acid comes in. So your hydronium ion donates a proton to your OH. Makes water. Water is going to leave again. And also, again, a pair of electrons from nitrogen will swoop in to make a double bond. Okay. So everything we've done up to this point in the mechanism has been exactly the same as we did from the last reaction. Okay. Also, though, here's where things get a little different. What did we do last time at this point to satisfy that positive charge? We brought in H2O, which did what? It deprotonated the nitrogen, right? Can we do that here? No. Why? Nitrogen ain't got no hydrogens. Right. So we have to do something else. Water still comes in and acts as a base, but instead of deprotonating the nitrogen, it's going to deprotonate this carbon, the one that's directly adjacent to your nitrogen carbon double bond. So it's going to take an H from here. These electrons will hop over there to form a double bond. And this pair of electrons will hop back over to nitrogen. And that's how you end up with your enamine. Name makes sense. It's part alkene for the ene. It's part amine for the, well, amine part enamine. Right? So the big difference is that last step. Okay. That makes sense? Great. Did that help?
Yeah. Thank you.
Okay. You can also try to predict the product with these as well. It's a little bit trickier than doing it with an amine, but it's still very possible. So if you look at the reaction setup here, again, basically, you can remove the oxygen and put a nitrogen in this spot, right? But the difference is you're not going to have a double bond here anymore. So you would have to put the nitrogen group over here and then move the double bond over here. So a little bit trickier than with amines, but still, pretty good. Okay. What else would you like to go over?
Do you remember which hydride sources don't, or like which weak hydride sources don't affect like the ketones? formation
I think I know what you're asking.
chemical.
Like which types of hydride sources will react with what type of reagents?
Yeah.
Yeah.
Like, which ones don't react with the
Sure. Yep, I can sum that up pretty easily. Like that. Aldehydes and ketones will react with strong hydride sources. Weak hydride, they will not react. Acid chlorides and esters. Strong hydride will react. Any other carboxylic acid derivatives? Oops. Getting ahead of myself. All right, acid chlorides and esters will react with both of them. Any other acid or acid derivatives? Strong hydride sources, yes. Weak hydride. No.
Which ones were the challenging?
Let's see, strong. That'll be sodium borohydride and lithium aluminum hydride. Weak. Dibyl H. And then there's one more, honestly, I can't remember the name of it. And it doesn't have an acronym. I guess I should probably look it up, Abe.
Tractor epoxy aluminum.
Yeah, that one. Matt, give me an acronym for that.
Leave it. Oh, no, LTBA.
LTBA? All right, sure. Matt, can you read off again what that stands for?
Lithium tritert epoxy aluminum hydride.
Lithium tritert butoxy aluminum hydride?
Yeah.
Yeah. We're going to call it LTBA. If you want the full name, you can look in the book, it's there. Honestly, since Dibyl H does the same thing, I usually just default to that one. You could use either one. Yeah.
Can we go over formation and hydrolysis of acetyl?
Acetals. Yep. Formation and hydrolysis of acetals. Okay. So you form an acetal whenever you have an aldehyde or ketone, and you react it with two equivalents of an alcohol or one equivalent of a diol, and then a strong acid. So let's say we had like, again, we'll just use acetone here. Okay, so this would be one example of an acetal setup. You can also use TSOH as your acid, right? Okay, so remember, anytime you form an acetal, there's basically kind of two phases or two stages of reaction. Each one begins with the action of the acid and ends with the reformation of the acid. So that's kind of a little, set of guidelines to sort of keep you on track, right? And really, if I want to be technically correct here, I should probably draw equilibrium for this. All right, so what happens first? Do y'all remember? Let me give you a heads up here. Ethanol or any alcohol is a very, very weak nucleophile. So weak, in fact, it's not going to be able to attack this carbonyl carbon as is. It needs a little help. How do we help it out? I remember. There was a way we amplified the partial positive charge on that carbon. Yeah. Remember, we're starting off with action of the acid, right? So sulfuric acid is going to protonate that oxygen. And that makes oxygen positive. Oxygen hates being positive. Oxygen's, it's that real moody kind of guy that just, wants to brood all the time, be all sad and stuff. Doesn't want to be happy. It wants to be negative. That's oxygen. So oxygen hates being positive, so it's going to pull on these electrons even more. It makes this partial positive stronger, strong enough for your alcohol to come in and attack. And when it does that, it'll move a pair of electrons up to oxygen. Gives you that. And what's the last part of phase one? HSO4 minus comes back in, grabs this proton, and you're halfway home. Okay, so a couple of things to look for at the halfway point. At the halfway point, you should have reformed your acid catalyst, and also you should have a hemiacetal, and that's what we have there. It has a structure that has a carbon with an OH and an OR. That is a hemiacetal. Right? That sort of gives you a little signpost to look for. All right? So that's the end of phase one. Now beginning phase two. What are we going to do at the beginning of phase two? Remember, each phase begins with the action of the acid. Your OH group grabs a proton. Right? And we've already seen that water is a good leaving group. And when it leaves, it creates a carbocation. All right. What happens now? What happens once you form the carbocation? What haven't we used yet? What's that?
The second
Second, yeah, the second alcohol, right? We have two equivalents. So we have another alcohol that can come in and attach itself. Sorry, I'm trying to be creative with my space here. All right, gives you that. And the last thing that happens is that you're going to deprotonate with HSO4. That will give you your acetal. And it'll also reform sulfuric acid. Any questions on how we got there? That makes sense? I'll let you guys finish writing. Then I'll show you how to destroy it. Because, of course, you noticed all the equilibrium arrows here. This is a reversible reaction. So we can actually go backwards with it too. All right, can I erase? Yeah. All right, so here's how you go backwards. Here's hydrolysis of an acetal. All right, and I'll show you actually just the same exact one so you can see how we got back to our original starting materials. All right, so when you want to hydrolyze an acetal, you need, of course, the acetal itself. You're going to need a strong acid catalyst, something like TSOH or H2SO4. And you're also going to need water in excess. That is very important to have in excess because the whole principle of this, the reason we can move in the direction we want, is because we're taking advantage of Le Chatelier's principle. So having excess water helps prevent formation of water through the mechanism. All right? Yes, ma'am.
So if there was an excess water, would the reaction not be?
If you, yeah, pretty much, yeah. If you had just like one equivalent of water, then basically what you'd end up with is you sort of reach an equilibrium between the acetal and the hydrolysis products. You'd sort of, I don't want to say half and half because equilibrium isn't necessarily half and half, but you'd have a mixture of both. Yeah, having access to water drives it to completion. You can look for the same guidelines. Same thing, you're going to have two phases. Each of them begins with action of the acid and ends with formation of the acid. The halfway point, you should have a hemiacetal, right? You're following the same path, just in reverse order, so the same milestone should be there. Right? How would we get started with this one? We know the acid's going to do something. What's it going to do? Yeah, acids love to donate protons, right? Pretty much the only thing that can accept protons here is oxygen, so let's protonate one of the oxygens. Okay. Now what? What's that?
That leaves. OH.
Ethanol is going to leave. Because remember, alcohols behave very similar to the water. So if water is a good leaving group, so is an alcohol. Leaves with carbocation. I'm going to go ahead and rectangle this ethanol because that is one of our organic products. All right, so what happens now to the carbocation? H2O. We have a bunch of H2O over there. That can come in. All right. So it gives them that. Now what? Last step of phase one. HSO4 minus comes in, deprotonates your O. And viola, you've recreated your sulfuric acid at the end of phase one, and you've also created a hemiacetal. So same halfway point. All right, so now we begin phase two. What are we going to do to begin phase two? What's H2SO4 going to protonate? What's that? It's going to be one of them. What's that? Yeah, the oxygen on your ethyl group will be protonated. Here's a question. Last time in the forward reaction, when we had this exact same situation, the acid protonated the OH, but this time it protonated this. Why didn't it just protonate the OH? Well, then we'd be going backwards, right? We're allowed to go backwards, except for the fact we already have an excess of water, so we don't want to make any more. So that's where Le Chatelier's principle comes in. All right, so you have this. Ethanol's going to leave because, again, alcohols are good leaving groups too. It's going to give you a carbocation plus the other molecule of ethanol, which just left. I'm going to put a rectangle around that because that's also a product. You end up with two equivalents of ethanol, which, if you remember in the last reaction, were involved in the reagents. Right? Once we get here, we can actually have a resonance form that we can draw where these electrons move into a double bond. And then the very last step is the HSO4 minus. Deprotonates that, and boom, you can see you have your ketone. So that's exactly what we did before, but backwards. And you can see we got our original acetone and two equivalents of it. Just to build the anticipation, upcoming in chapter 22, there's a mechanism really, there's a couple of mechanisms really similar to this. Can't wait. It's how we make esters. Got a few minutes left. Is there anything else you guys would like to ask?
which compounds do the organocuprate not react? Is it-
Oh, okay. You want to just do the same thing that we did
Yeah.
before? Okay. Let's put just organometallics. All right. All right, so aldehydes and ketones, I want to use R and T to represent organometallic. They react with strong organometallics. But not weak ones. Acid chlorides. They react with both strong and weak. Let's see, esters. They react with strong organometallics, but not weak ones. Let's see. All other acid derivatives. Do not react with either one. At least not in the way that you would want them to. Need more of an acid-base reaction. But for your purposes, you can just essentially think of them as not. Oh, strong. That's going to be your organolithiums and your Grignard reagent. Weak. That is your organocuprates. All right. All right, we are actually a little over time. If you have any other questions, just feel free to get in touch with me. I'll be in my office for the rest of the morning, although I will be on a Zoom call from probably about 10 to 10:30-ish or so. But yeah, just feel free to send them to me or drop by. I'll be happy to try to answer. All right. Okay, let me stop the recording here real quick.